Let's take the time to look at graphing logarithmic and exponential equations and functions. So far we've only really looked at logs, analytically, and same with exponentials, but with graphing them we can really see kind of their tendencies for different values of x and kind of the the patterns that we kind of see once we graph them. So if we look at y equals log x, that's this kind of curve in red here. The blue curve is y equals 10 to the x, and kind of this curve straight along here, that's y equals x. And you might be wondering, well, why did you bother putting in the y equals x one? Well, it's because you can see, we talked about before that logarithms and exponential equations and functions are inversely related. They're considered the inverse of each other, and let's remember the definition of the inverse here. So if we have y equals log x, remember there's an imaginary 10 here. So if we get this into exponential form, this is basically saying 10 to the power of y is equal to x. Well, with this blue function here, y equals 10 to the power of x. So you can see how we're effectively just switching the x and the y in each respective equation. And that's why they're both kind of reflected along this green line. Okay, so we can see for the exponential as x gets bigger, right, the blue function increases exponentially. So it's kind of like a parabola looking shape, except it's even steeper, even more extreme. So exponentials have a horizontal asymptote, right, and they kind of shoot up like this. Okay, so for example, if this is 10 to the power of x, we see that if we had 10 to the power of 0, we would get 1. If we moved 1 over, we would keep going up. 10 to the power of 1 is 10, so it would be somewhere up here. And I didn't have room to graph all of them, but you kind of get the idea. So it kind of shoots up super quick. So every square we move over, we're multiplying the previous height by 10. So this one was 1, the next one's going to be 10, the next one's going to be 100. It's going to shoot up really quick. Now with logarithms, it's kind of the opposite. It's as if we took this blue curve and kind of flipped it, or if we kind of rotated our axis, right? If this is our new x-axis, this is our new y-axis, we can kind of think of it as an exponential function. So we move over to the left. If we flipped it, we moved over, let's say 1 space, we would have to go to the right 10 spaces now. So that's kind of how you could look at it in terms of inverses there. And it's the same thing with different bases. So if we have the log of 5 or the log of x in base 5, this is kind of the inverse to 5 to the power of x. So if we look at this first logarithmic equation, that's basically saying 5 to the power of y equals x. Well, the second equation there is saying 5 to the power of x equals y. We've just switched the x and the y. So exponentials and logarithms are inverses of each other, and they're reflected perfectly in the y equals x axis, because if you take one x value and switch it with the y, you're going to get kind of the other one. So see here how if we start at 0, if we move up 1, it's kind of the opposite. We're going to move to the right 1, right? And say, see how if we go to 2, we're going to get to about, if we go to 2, we're going to go kind of up, I don't know, we're going to go to the right, what is that, 0.4. Well, for this one, if we go 0.4 to the, hold on, if we go if we go 1 full unit to the right now, we're going to go up 0.4. So it's kind of opposite. For every direction we move, say we move to the right here by 1 unit, we're going to go up. That looks like, I don't know, 0.7 units. Well, for this one, it's a bit of the opposite. We're going to go up 1 instead of the right 1. And if we go up 1, we're going to go to the right about 0.7 units. So they're related in that way. And you can see how they're also reflected if we drew a straight line kind of right to this point right here, right to this point right here. They kind of make, they're symmetrical along the line of y equals x. That's kind of what I'm getting at. And you can see that once we graph it, it just might be not intuitively obvious when we're solving it with just equations, right? It's always nice to see these graphs. And same thing with the natural log of x. So the natural log, remember, is just the log of x in base e. Okay, so if this is equals to y, we can say e to the y equals x. That's kind of the same thing. And then the second one, e to the x equals y. We're just switching the x and the y. and that's how it's reflected. So logarithms, they kind of follow the shape where they kind of flatten out, but they still increase as x increases. And the exponentials do as well. They increase as x increases, but they increase much faster. So they kind of all follow the same shape. It's just the steepness of them is dependent on their bases. So if their bases are bigger, then the exponential is going to be steeper and the logarithm is going to be kind of shallower. And if the bases are smaller, then that means that the exponentials are going to be kind of shallower, not as steep, and then the logarithms are going to be a bit higher. So the logs are going to increase faster. They're inversely related in that way. And we can also see how we can solve systems of equations by kind of graphing both functions and calling one side of it y. So if we call both sides y, then we can graph y equals log x and y equals 1. Okay, and once we do that, we can see where they intersect. That's going to be a solution. So if we were to solve this algebraically, we would say y equals log x, y equals 1. So then we could say log of x equals 1. Remember this, there's an imaginary 10 here. So 10 to the power of 1 is equal to x. So x equals 10. And once we solve this algebraically, we can see that where they intersect, if we graph both functions, they intersect when x is equal to 10, which is what we just found. And to find the y value, we just plug that back in. So we would get the log of 10, right, because x is 10, and we would just get 1. So that's how you could figure that out graphically, is if you have a logarithm and a constant, or a log and a log. If you're trying to solve a system of equations, you don't always have to do it algebraically. You can go on Desmos or whatever you want to do, graph both of them and treat them as a function, and where they intersect, that's going to be your solution. Okay, so on the grid below, sketch 2 log x plus 2 using transformations. Okay, so a bit of a new concept here is transforming logs. So whenever we're transforming, we always want to think about what we started with. So if our base function is y equals log x, okay, then that means that we're going to kind of draw that flattened out shape there. So we know that there's an x-intercept at 1. So we're going to draw it right here, right? And we know that there's kind of a vertical asymptote. That's one property of logs at x equals 0. So I'm just going to kind of draw that there so we can see it. Perfect. And now we're going to kind of turn it sideways and treat it like an exponential. So we move up 1, we're going to go over 10. So we're going to be right here, and then we move up another one. We're going to be over 10 times 10, so it's going to be over 100. It's going to be pretty steep. So we can't really draw a ton here, but it's going to be kind of this, this sideways looking. Yeah, it's going to be tough to draw here. This sideways looking thing like that, and it's going to flatten out. So it's going to go down to infinity, and it's going to kind of keep going up to infinity, but at a really slow rate. So all we want to do here is transform it. So 2 log x plus 2, whenever we see the argument has something different, instead of x, it's x plus 2, we take every point and we shift it 2 to the left. And even before that, we see this 2 out in front, so we multiply every point we see before by 2. So if this before was 10 and 1, it's going to be 10 and 2. We're just kind of multiplying every point by 2, right? So we just kind of keep going. I don't know the exact points, but it's going to look something like this. There's still going to be an intercept here at 2, and this is probably a bad approximation, but you would have actual better points to use. I did a bad question because this shouldn't be a base 10 log. It's kind of hard to draw, but you kind of get the idea. So it's going to be kind of doubled every single point, and it's still going to come down and hit right there and go down to negative infinity, and it's never quite going to hit 0. We still have to account for this x plus 2, so every point we see here now, we're going to go 2 to the left. So it's at 10 here, we're going to go to 8, right? And, we just kind of keep doing this. The new vertical asymptote is going to be at negative 2 for the x. And if you were to graph it, you would just kind of do the same thing every point. Oh my gosh, it's transformed 2 to the left. So it's going to look like I'll draw it a bit better. Then the new x-intercept would be at -1, right? Instead of +1 because we're shifting 2 to the left. Oh my gosh, holy smokes. There we go. Good enough. So you kind of get the idea. Now the next one here, sketch y equals 0.5 times 2 to the power of x minus 1 minus 3. So if we were to write this out, this would be y equals, I know it's kind of hard to, I should write a half. 1/2 times 2 to the power of x minus 1. And then this is minus 3. Okay, well, if we're looking at 2 to the x, right, that means we'd go over 1 up, or sorry, we would have an intercept at 1, a y-intercept of 1. We would go over 1 up 2, because 2 to the 1 is 2. Then we go over 1 again, 2 to the power of 2 is 4. We go over 1 again, 2 to the power of 3 is 8. So we're kind of getting a base function here. 2 to the power of 4 is 16. 2 to the power of 5, that's 32. And you get the idea. We just kind of keep going like this. There's a horizontal asymptote right there. And you kind of draw your exponential there. Okay, hope that makes sense. And then if we're transforming it, we just multiply every point by 0.5 and shift it to the right by 1 unit because it's x minus 1, and shift it down by 3 because it's minus 3 at the end. So let's use x equals 0. Let's go 0.5 of that, right 1, down 3. So we go 0.5 of that right here, right 1, which is right here, and then down 3. So that'll be 1, 2, 3. So negative 2.5 it looks like. And then we kind of keep going with all of our points. So let's do x is equal to 1. So we go 0.5 of that, which is at 1. We'll move it 1 unit to the right and 3 down. So it's going to be at negative 2. Okay, and we kind of see the next one here. If x was 2, we'd go half of that. So 2 to the power of 4 is only 2. And then we'd go right 1, which is right here. And then we go down 3, so it would be right there. And you can see how it's kind of a bit shallower. That's because we're counting for that 0.5. And if we were to say x is equal to 3, that would be 8, so we'd go half of that. And then we would go right 1, and then we would go down 3. So 1, 2, right here. And just to do the last one for you here, half of 16 is 8, so it would be right here. And then we would go right 1, and we'd go down 3, so 1, 2, be right here. And we can kind of see how it's 0.5, kind of as shallow as before, and it's going to have an asymptote at whatever this value right here is. So it's going to have an asymptote at negative 3. Okay, and then, sorry, cut that off there. So that was at 8. And the asymptote's at negative 3, so it's kind of going to come from here. Going to cross through these points and look like this. Going to be half as steep as the one before. Okay, last one here. On the grid below, sketch y equals 0.5 log in base 3 of x and use it to find the graphical solution for y equals 1. So basically, we're going to treat both of these as functions, which they are, and call them y. So we're going to graph 0.5 of log in base 3 to the power of x. Okay, so what we're going to do is, we can think of this as y equals 3 to the x, just the inverse of that, right? So we can kind of start at 0 and say, well, if this was just y equals 3 to the x, we have to turn it. So every kind of point we go over 1, which is really up 1, but we can say we're going over 1, we're going to go up in our kind of new rotated axis by 3. So we're going to go over 1, up 3. With logs, it's the opposite, but kind of bear with me here. And then we can go over 1 again. So 2 to the power of 3 would be 8. So this would be here because we go over 2 and up 8. Notice how you should be confused because this isn't really up 8. It's to the right 8. But remember, we're talking about logarithms, so they kind of follow this weird flattening out shape. And that's because it's the inverse of an exponential. We have to rotate the axis to kind of visualize it. And now 3 to the power of 3 is, hold on. So this would be 3 to the power of, oh, hold on, this would be 3 to the power of x. Yeah, so this would be 3, this wouldn't be 8, this should be 9, sorry. Because 3 to the power of 2 is 9, and 3 to the power of 3 is 27, so it's going to be kind of somewhere over here, and you can see kind of the sideways exponential, which is really just a logarithm. And what we do is we plot y equals 1 as well, so if 1 is kind of along this line, that's the y value. We can see, I'm going to move it down a bit, we can see where they intersect, and that's going to be our solution. So if we zoom in, they're going to intersect right here. So the kind of solution for this answer would be a coordinate. It's going over 3 and up 1, so it would be 3 and 1. And if this is a system of equations, let's just verify our solution quickly. Make sure it works for both of them. So we're saying y equals 0.5 log in base 3 of x. Well, we said y was 1. 0.5. Oh, I didn't account for the 0.5. That's a bit of an issue. Okay. Didn't see that there. So 0.5, we just multiply, or kind of divide each point by 2. So that's going to be there. That's going to be there. That's going to be around there. Hold on. Yeah, it's going to be somewhere. Let me just see here. So x, I'm just checking this out here. So 1, so x was 9. Yeah, okay, that looks good. Sorry about that. So this is going to be half of this point, we can kind of just multiply all of them by 2. I'm just kind of guesstimating, but you get the idea here. And we're going to transform it so it's 0.5 of the original one. And kind of caught me off guard as well. Actually, this isn't completely right because we have a vertical asymptote as well we got to account for. So this is going to look like this. Oh man, my logarithms are not looking good today. Please bear with me. Logarithms are not the easiest to draw, to kind of cross all the points. So we've transformed it now, accounting for that 0.5. And we can see now that the real solution would be 9 and 1 for our coordinates. So 9 and 1, let's just plug that in, make sure it's good. So we're saying 1 equals 0.5 log in base 3 of 9. Well, this 0.5 here can really be moved to the 9. So we're saying 9 to the 0.5, which is just 3. So 1 equals the log in base 3 of 3. We're saying 3 to the power of 1 equals 3. That is true, so that system works, and y equals 1 is kind of independent, is independent of the x, right? So we know that that's right. So this coordinate here, solving algebraically, we can kind of determine that the coordinate 9 and 1 is going to give us our solution for this system. So apologies for my bad drawings of logarithms, but that's how you would solve systems of equations and kind of analyze logs and exponentials graphically. So sometimes it's harder to think about how to solve problems where there's a bunch of functions and equations going on and you don't really want to tackle them algebraically. So let's say you had I don't know, the log, or I'll go 5 times the log in base 3 of x minus 8 minus 4 is equal to 1/2 times the log in base 9 of, I don't know, something weird, 2x minus, or plus 1, right? You have to solve this for x. Well, what you would do is you would just treat either side like a function. So you would say y equals 5 log 3 of x minus 8 minus 4. So that's going to behave, the way we just saw with logarithms. We don't know exactly how it's going to look, but we have a decent idea. And at some point, that's going to equal the same value as the function y equals log in base 9 of 2x plus 1 plus 1. So hopefully they some point intersect. If they do, there's going to be a solution, but if you treat each one as a function and call it y, graph both of them, where they intersect is your solution. So the x-coordinate is your x value, and we're not too concerned about the y because notice how the original question didn't give a y, they only wanted the x. So that's what you would solve for, but I hope that makes sense. And that kind of concludes my little series on logarithms and exponentials. So I hope you learned a lot, and it was fun talking about it. Thanks for listening, and I'll see you soon.